For the second part of this pre-lab, we are going to be using a little bit this PhET simulation, which is about balancing objects on essentially a seesaw, which is very similar to what we're going to do in lab this week by finding the center of mass of an object and trying to balance it around its center of mass. So this is the page that you'll be taken to. We are going to use the balance lab. You can also come over here and play a little fun game to test your understanding of center of mass and balance and static equilibrium, if you would like to do that too. So I'm going to click on the balance lab here. And what you see is we've got a seesaw and it's got a pivot exactly in the middle of it. And right now it's resting on two pillars, but we can remove those by clicking this button down here, okay? And then up here, I'm gonna click the level, which will tell me whether or not everything is in equilibrium. So if everything is level, then everything is in equilibrium when we place masses onto this seesaw, essentially, okay? So what we're gonna do, I'm gonna put the ruler on as well so we can see the distances at which we're placing our objects away from the center of mass. So what we're going to do is we can take some of these masses and place them on the seesaw and see what happens. The first problem that we're going to walk through after you see this is one where I'm placing a 5 kilogram mass here at 1.5 meters to the left of the pivot here. So I've done that. And of course, we are not in equilibrium. So you saw when I put that mass on there that the system wanted to swing in this direction, okay? Wanted to swing down in this direction. So it's swinging down in the direction that we call, when we're thinking about torque, which you'll learn about in a minute, we call that direction counterclockwise. So it's falling opposite the direction that the hands go around the clock. So this is a counterclockwise torque that's being exerted here, okay? Now I need to figure out where I need to place another mass over here on the other side of the pivot in order for everything to be balanced, everything to be in equilibrium. And when things are balanced, then the center of mass of the system is exactly at the pivot point here, and that means that the sum of all the torques in our system equals 0. So I'm gonna place, let's see, you can experiment to see what mass you need to place on here and where you need to place it in order to see how you can get it to balance. So let's just do a little experiment. Let's take my 15 kilogram mass and see what happens. Oh, it didn't want to balance at putting it at 1.5, of course. Okay. If I place another 5 kilogram mass at 1.5 meters, I am going to balance the system because I have the same torque on the left as I have on the right. Okay, so let's see. If I put a 15 kilogram mass here at 1.5 meters, you see that the torque acting from this force that I'm applying, which is the weight of this object, that torque wants to pull my seesaw in the clockwise direction, in this direction, okay? So I don't want to put the 15 kilogram mass there. Where can I put it so that it balances everything? Well, oh, looks like I can put it here. At 0.5 meters away from the pivot, I can place my 15 kilogram mass in order to balance my 5 kilogram mass on the other side, which is sitting at a distance of 1.5 meters away from the pivot. So what's happening here is that we have something called the torque. The sum of the torque on both sides of these equations, the sum of the torque must equal 0 in order for us to be in equilibrium. Also, then that means that the center of mass of my entire system, if I calculate the center of mass, is going to be sitting right here at the pivot too. Okay, so let's see. I can also place a 10 kilogram mass somewhere on here to make everything balance. Let's see. Oh, I probably need to bring it closer in. So I can place my 10 kilogram mass here at 0.75 meters away from the pivot, and in doing that, I can also balance my system around the center of mass here, okay? So we're gonna walk through a problem to figure out what distance do I need to place this 10 kilogram mass on the opposite side of the pivot here in order to balance my 5 kilogram mass on the other side. So we just did the experiment, and we are going to do the calculation by thinking about torques, this thing I've been talking about this whole time.
We have a wooden plank here, that's what this is, resting on a wedge, which serves as what we call the pivot point. And this wedge is directly in the center of my plank. This is also the center of mass of my plank. Okay, so right here is the center of mass of my plank. I'm going to get everything to balance around this center of mass right here. Okay, so what I'm going to do is I'm going to place a mass of 5 kilograms, 1.5 meters to the left of my pivot point. Where do I need to place a mass of 10 kilograms on the right side of this pivot point in order for my system to balance? Okay, so I've got my first mass, 5 kilograms, sitting at a distance of 1.5 meters from the pivot. I have my second mass of 10 kilograms sitting at a distance of I don't know what from the pivot point. I need to figure out how far away do I need to place it on this side so that my whole system balances, so that my whole system is in equilibrium. Okay, so everything is going to be balancing around this central point. Okay, so in order for our system to be in this equilibrium, we call it the static equilibrium, we are going to think about torques in order to solve this problem. And we want the sum of all the torques in our system to equal 0. If the sum of all the torques in our system equals 0, then our system is in equilibrium and everything will perfectly balance. Okay, what is torque? We haven't talked about torque yet. Torque is the rotational equivalent of a force. So a torque is equal to what I'm going to call R times the force times sine theta. Okay, this R is the distance from our pivot point where we're having everything rotate around. So R is the distance from our pivot point to the place where our force is being applied. So F is our force, and theta, that's the angle between my force vector, the force that's being applied, and a vector directed from the point of application of the force to the pivot point. Okay, so we need to think about torques in order to solve this problem. The sum of all the torques in our system need to equal 0. All right, so let's think about the torques that are acting in my system. Well, let's just go ahead and draw the free body diagram here. Okay, so we have the normal force here of that pivot pointing up on my, my plank. And I've got the weight of my plank downward. So that's, I'll call it the mass of the plank times gravity downward, okay? And then I have the weight of my masses here, okay? I've got the weight of my mass downward. We'll call that M1G, and I've got the weight of my second mass downward. I'm going to call that M2G, okay? So the thing that is causing the torques in our system are the weight of these two objects that I'm placing on either side of the pivot point. If you place something at the pivot point, so the mass of my, or the weight of my plank is resting directly on the pivot point. If you place something directly at the pivot point, there is no torque because there's no distance between where that force is applied, which is the weight of the object. But we do have these two masses, which both have weight, and they are contributing to the torque in our system, okay? So the forces in my system here, for thinking about the torques, are going to be the weight of these two masses that I'm placing on either side of the pivot point. And so their forces are going to be their weight, their mass times gravity. Now, torque also has a positive or negative sign. Let's see, so this angle here is the angle between our vector that we can draw from the pivot and where a force is applied and the force itself. And for both of those, you know, our distance r here, that vector that we could draw between the pivot and where that force is applied and my force, they both make a 90-degree angle with each other, okay? So 90 degrees is just 1, so we don't really need to worry about that. We'll just assume that that's 1. But there's a sign convention on these torques. So we say that a torque is positive if it is acting in a counterclockwise direction. A torque is negative if it is acting in a clockwise direction. Okay, so let's think about the torques in our system. How do we figure out whether or not these torques are clockwise or counterclockwise? Let's start with this one right here. So how you think about it is, let's say I remove this second mass, I only have this mass right here. If I place that mass on this plank on its own, which direction is my plank going to fall? So if I just put this mass on, remove that second mass, put this mass on, my board is going to want to fall in this direction. It's going to fall to the ground this way. So that means that my torque is acting in this direction. Okay, so that's the torque. This is a clockwise torque. It's in the same direction that our clock runs, clockwise. So that means that we have a negative torque for the torque acting on this side of the pivot. So my physics professor used to always say that when you're thinking about torques, clocks are wrong. So if clocks are wrong, then the clockwise torque is negative. Over here, for this mass, if I remove this mass over here and see if I put that mass on, which direction will my board fall? It will fall in this direction, this way. So this motion here, falling this way down, is going to be opposite the direction of the hands on the clock. So that is going to be a counterclockwise torque, and so that is a positive torque. Okay, so if we think about the torques in our system, we've got two that are contributing to the sum of torque equals 0. We've got the torque coming from this first mass and the torque coming from our second mass. So if we do, the sum of our torques has to equal 0, then for my first mass, we saw that that's a positive torque. So I'm going to have positive m1g, that's the force applied, times the distance that is placed from the pivot, and then minus our other torque, which is a clockwise torque, okay, minus that torque, which would be minus m2g, the weight of this object here, times r2, its distance away from the pivot, and that has to equal 0. So we're trying to solve for where do I need to place this mass in order that my system balances. So if the sum of my torques equals 0, then my system balances. So I need to solve this equation for this distance that I need to place the second mass, okay? So we've got m1g_r1 equals m2g_r2. Well, g cancels out on both sides, so then my equation says that the radius I'm looking for is equal to the mass 1 times its distance from the pivot divided by mass 2. Okay, so mass 1 was 5 kilograms. Its distance from the pivot was 1.5 meters. And we divide that by mass 2, which is 10 kilograms. Okay, so then we find, plugging in those calculations, that we have to put our second mass of 10 kilograms at a distance of 0.75 meters away from the pivot in order for this thing to balance. And so you can check that in the PhET simulation. You can check this exact problem in the PhET simulation in order to see if you can see what it looks like, see what happens when you move the masses around, to verify that our system would balance the system that I've described here if I place my mass at 0.75 meters. Now, you're not going to be able to test the numbers that I'm going to give you for this particular problem, but you can check it for the one that I just talked about right here.
We can also do another experiment. There's a bunch of different experiments we can do here. But let's say I'm going to be asking you to find the mass of a mystery object. here are the mystery objects. If you click on the arrow here, you'll get these little presents that are labeled A, B, C, D, and then here we have E, F, G, and H. So all I'm going to tell you, all I'm going to ask you is to tell me the mass of one of these mystery objects. Okay, that's all I'm going to tell you. So you have to do an experiment to figure out what is the mass of this mystery object, and we're going to think about torques in order to do that too. So let's just grab one of these mystery objects. Let's grab A here. Okay, and I'm going to place it right here at 1.5 meters away. Well, it doesn't really matter where I place it. I'm just going to put it somewhere on here. And then I'm going to play around until I can balance this mass and put it in equilibrium. So let's see. I'm going to come over here, and there's any number of combinations of ways you can do it, right? So let's see. If I put my 15 kilogram mass here, I'm still not doing much to balance. Oh, there we go. Actually, okay. So you can just kind of experiment and play around. You could even move your mystery object around. But I found that with my mystery object A at 1.5 meters away from the pivot, I can get it to balance if I put 15 kilograms of mass at 2 meters away from the pivot. So we can use this information knowing the mass of my second object and knowing the distance away from the pivot for both of these objects in order to calculate what must be the mass here of my mystery object. Okay, we can figure out the mass of the mystery object by performing an experiment to see, knowing one other mass, where can I place those masses around the pivot in order to make it balance? And using that information, then I can get at the mass of my mystery object.
You are going to grab a mystery box, you don't know the weight of it, and you're going to experiment to figure out where you can place that mystery box and where you can place other masses of known mass in order to balance that system. Then once you're balanced, you can take the mass of those additional masses that you put on the balance, and you can take the distance that those objects are away from the pivot point and use those to solve for the mass of the object. Okay, so let's say I've got my PhET simulation open. I ask you to find the mass of mystery box A. So what you're going to do is we take that same problem that we just solved in the previous problem. We take that same equation that we just solved in the previous problem here. We take the sum of the torques from both of our objects. They have to equal 0. So this is the equation that we just derived. But now instead of solving for the distance that we need to place that second mass, we're going to figure out, if we know the distance at which we placed both of our masses from the pivot, and we know the mass of one of those objects, we can figure out what the mass of the second object is. So I just need to solve this equation for M2. So M1GR1 equals M2GR2. Gravity cancels on both sides. And so this time we're solving for the mass of the second object. M2 equals M1R1 over R2, okay? So we can figure out what the mass of the second object is. We know the mass of the first object that you've placed. We know the distances that you've placed both of those objects on either side. And then you can find the mass. Now this only works after you've done your experiment. You've moved different masses around. You've changed the position of those masses with respect to the pivot until you found a combination that works to get your mystery object to balance. Once you find that, then you just plug in the values that you're given in order to figure out what must have been the mass of that mystery object.